Thank you for introducing me. So today I'm going to talk about fighting fraud, finding duplicates at scale. First, a few words about me. Originally, I come from software engineering. Like my original background in software engineering. I worked for a couple of years as a Java developer. Then I decided to switch into data science. I did a master's in business intelligence. Last year was in Berlin, and I decided to stay in Berlin. And since 2015, I've been working as a data scientist full-time. First time I got into this problem of duplicates was a Kaggle competition a few years ago, organized by Avito. Avito is the largest classifieds website in Russia. So they had this problem of duplicates, and then they asked the community to help them to detect duplicates using machine learning. I did pretty well in that competition. Since then, many people found me, many companies found me on the leaderboard, contacted me asking for help. I did help a couple of companies. So I want to summarize all this experience and present it here. And also, the talk today will be not about how to do well in a Kaggle competition like this, but rather what are the next steps. Okay, now you did well on Kaggle. What is next? How to use this? So that's me 1 year ago. So this logo there is OLX Group. And OLX Group, probably many people here who are from Germany didn't hear about this. This is actually quite a large company. Like this is a like parent brand for many classifieds websites. So Avito is one of them. I already mentioned they hosted that competition on Kaggle. So this is the largest classifieds in Russia. Then OLX itself is classifieds website in a bunch of countries, like in many countries like Poland, Ukraine, India, Kazakhstan, quite a lot of countries. And Letgo is also third big brand under OLX Group. This is large classifieds mobile in the States. So today I'm not going to talk about specifics of the system that we have at OLX, but rather about the general approach. I want to start the presentation by talking about user-generated content. So user-generated content is content generated by users. So there is a website, can be a blog post, can be a social network, can be a classifieds website where users can post content. So user can come to this website and create a post about a dog. Then write something, this dog is so nice. Then they can get carried away, like they love this dog so much. Or if it's a classifieds website, maybe they want to sell this dog. So they can create multiple listings and basically spam the platform. Or they can post something not appropriate on the platform. Or maybe something illegal. In case of classifieds, they might try to sell something that they are not supposed to. So there is a bunch of problems with user-generated content. Especially fraud and duplicates. So these two things, fraud and duplicates, they often come hand by hand. They are not always related, but often they are. Typically it happens like this. So somebody goes to the platform, for example, classifieds, and wants to sell something, a dog. And then a fraudster comes. The fraudster copies the picture and waits till the ad disappears. And then they post another listing with the same image, maybe with a better description and better price. And then somebody comes to the platform. Okay, nice dog, I want to buy it. They call the seller. And the seller says, yeah, you know, there are like 10 people in front of you in the queue. They all want to get this dog. But if you give me $100, I'll reserve it for you. And he gets the money. And disappears. And the buyer is very unhappy and frustrated. So how can we help them? How can we prevent it? Instead of just letting users publish everything they want, we should first look at what is there and decide whether it should be allowed or not. For that, there are content moderation systems. They might look like this. So user posts something, and then there is automatic moderation system that looks at this and uses machine learning to decide is it suspicious or not? And then they can reject it right away, saying, okay, this is not allowed. They can accept it, saying it's fine. Or in many cases, when the situation is not clear, we can ask people, to ask. So moderators are actual people who have some kind of interface to look at these items from the queue and decide to make the final decision whether it should go live on the platform or not. This automatic moderation system may contain multiple components, like a system for detecting explicit content, a system for detecting forbidden items, and a system for detecting duplicates. So this is what I'm going to cover today. I already gave a talk about duplicates. So that talk here, you can follow it, like there's a link. It's more about methodology, like how to do well on a Kaggle competition. So this talk, as I mentioned, is slightly different. It's about the system, but still there's a lot of useful information there, so you can have a look. In summary, how to approach this problem. So it's a two-step problem, so you can approach it with 2 steps. First step is you select candidates, something that is not necessarily duplicates, but could be duplicates. And ways to do this is, okay, you have an ad. What are the other ads published in the same category? Or what are the other ads published in the same city? What are the other ads published by the same seller? What are the other ads published from the same IP, from the same device? So this is not necessarily duplicates, but there is very high chance that they can be duplicates. And then on the second step, from all these candidates, we actually use machine learning to find what are the real duplicates there. And what we do is we get all these candidates from the previous step, and then we ask people to look at them and say, okay, is it duplicate or not? So people say duplicate or not, and we get this training data, which consists of a pair, ID 1, ID 2, and label 1 if it's duplicate, label 0 if it's not a duplicate. And then we can compute all kind of features from this, then throw it into a machine learning model, and then this model will actually help us find duplicates. Features can be pretty simple, like, okay, what is the absolute price difference? What is the relative price difference? Is it published from the same IP? What is the distance between these 2 listings, same location, is it same category? We can also look at similarity between 2 titles. Okay, are these 2 titles similar? Are these 2 titles different? Basically, these are all features that we will use in the model. It's quite important when we have images, like in classifieds case, to look at them as well, because an image is worth 1,000 words. And especially in classifieds, buyers want to look at the item before deciding, okay, do I want it or not? With images, hashes are a very useful thing because they summarize the entire image into a simple byte string that we can use for comparison. There are multiple types of hashes. First category of hashes is cryptographic hashes. So these are general purpose hashes like MD5 that are needed to detect if file was modified or not. So for example, in case of MD5, if we take a file and change just 1 bit of this file, it will result in a completely different MD5 hash. These hashes are useful in duplicates, but only to detect byte by byte exact matches of the same images. There are other kind of hashes. They are called perceptive hashes. So these hashes, when you change only, if you open the image and change only 1 pixel with Microsoft Paint or whatever, Paint, and save it, it should result in the same hash. So in this example, so we changed the image slightly. That resulted in a completely different MD5 hash that we have on the bottom, but the hash, which is a perceptive hash, stayed the same. And there are many hashes like this. So the way it worked, they work. I will not go into the code. I'll just explain how they work. This is the hash. So we have an image. We then break it in multiple cells, and then for each cell we calculate the average pixel value there. And we see that for the area where the image was modified, the value is different, the rest stays the same. And then what we do next is we compute the difference between second column and first, third column and second, and so on. So we have this bunch of differences. And then finally we just consider if it's greater or 0 or not. So we have a bunch of Boolean variables, binary. And then we can think, okay, we have this Boolean array. Let's treat this as bits and compress it into one digit. Like each row of one bit becomes of 8 bits, becomes 1 byte image, 1 byte integer, and then we can basically represent each integer as a hash, put them together as a hex, put them together and get a hash. Other hashes, other perceptive hashes work quite similar to this. And then these hashes, since they are perceptive, so they have this nice property that small modifications in input lead to small modifications in output. We can use them to compare two images. We can just look at how many bits are different, and that will tell us how different these images are. This is a quite useful feature. But what is more, we can use these hashes to actually select candidates. We can say, okay, what are all other listings that have the same image? And that will give us a lot more candidates to consider. We can go deeper and include, also use neural nets. And like in any convolutional neural net, we have this layer before the final prediction, usually called fully connected layer. And this is typically used to extract so-called image embedding. So this is like a vector representation of an image. So we have an image, and it gives us a NumPy array that represent this image. They have nice semantic properties that two similar images have very similar vectors. So this is an official example from Keras. It's pretty easy, just like 10 lines of code that give us this representation. This example, however, uses VGG, which is quite heavy. It's like half a gig model. Typically, like it's not worth it. They are slow, they are heavy. There are lighter models like MobileNet that are, I don't know, like 25 times smaller. And they have similar accuracy, and the embeddings that we get from MobileNet are similar, have similar properties. So it's better to use them. It's like, again, the code is pretty simple. So, okay, we get MobileNet, we extract features, but this gives us quite large vectors. So in this case, it's more than 1,000. What do we do with this next? What we can do is take this large vector and use simple dimensionality reduction techniques like singular value decomposition or PCA to reduce it to something more manageable, like 100 dimensions. But then from that, we still want to compute hashes, because hashes are nice, easy to deal with. And for that, we use LSH. LSH is locality sensitive hashing. This is a family of hashes. A perceptive hash that we covered previously is also LSH, because they have this nice property that a small change in input results in a small change in output. So just an idea, one of the hashes of LSH, it's called random projection. They are built on this idea that if something is close in the regional space, when we project, it stays still close. If something is far, when we project, it's far. So we just generate random vectors, we project on them. In this case, 2 cars are still close, or 2 animals are close. And then we can generate many such vectors and project on them. So this is the basic idea for random projection. It's very easy to implement. So we generate many projection vectors, store them somewhere. We do it only once. And then for each image, for each vector that we have, we use these projection vectors to calculate hashes. And then we store them somewhere. Where to store? Of course, Elasticsearch. So why Elasticsearch? Elasticsearch is implementation. It uses Lucene to implement inverted index. Inverted index, so like in case of direct index, is when by ID, sorry. Direct index is when from ID we can get a document. So, like, for example, we have image ID1, and we use it to get the actual image. But inverted index is the other way around. We can ask, okay, for this hash, what are the images? And this is exactly what we need for this problem, because we want to find all other listings that have the same image that has the same hash. So we can just throw everything into Elasticsearch and it will give us the answers. We can also go further and instead of just using the exact match, we can chunk the hash into 4 or 5 chunks and then tell Elasticsearch, hey, this is a usual string. Treat it as a usual string because Elasticsearch is a system for text search. We can build on top of that, saying, okay, treat it as a string, as usual tokens, as words, and then look for this. And then when we do this, when we search using such queries, then first it will find exact matches, then matches where 3 out of 4 tokens match, then matches when 2 out of 4 tokens match. We can index everything, like every item that we have, we can index in Elasticsearch. And to find duplicates, we can use more like these queries, saying, hey, I have this document with this ID. I want to find all the other documents that are similar to this. And then we don't just use hashes, we can put title, description, all the textual fields, and say, okay, I want, like using Elasticsearch, we can also say, I want title to be 2 times more important than other fields. So this is very useful, and we can use this to get candidates. So how to actually do this? Now we have this idea that we have hashes. How do we put them to Elasticsearch? What is the big picture? We can build a system for indexing everything. So a user creates a listing, and this listing is stored somewhere. Image can go to S3. S3 is storage from AWS, where we can keep files. So image gets to S3. Then every time you put something to S3, S3 generates an event saying, hey, something was put to this bucket. So this is the bucket name, and this is the name of the file that was put there. Then a Lambda function, AWS Lambda function, can listen to these events coming from S3. And okay, there is a new file. Let's fetch it and calculate some hashes. So with just these 4 lines of code, we can already compute all these hashes. There is a library for that image hash. It's simple as simple as that. Then we put all these hashes to another queue, and then eventually it goes to Elasticsearch. So it looks like this. So why do we need an extra step from Lambda to Elasticsearch? Not directly, because in case there is a peak, we don't want to kill Elasticsearch with many inserts. So we want to pace it out. That's why we have a separate component in between. And Lambda really scales. So it really takes away all this complexity of scaling up and down. And in peaks, like when we have, for example, 200 invocations per second, it just scales. There is nothing to worry about. And there is no invocation, it goes down, of course. And we can process this way like 10 million images per day. Of course, we don't always just insert into Elasticsearch. We also need sometimes to delete things. Similarly, we can subscribe to delete events from S3 and also have another component that updates records in Elasticsearch saying, hey, this thing was removed from our storage. Also covered neural networks. We can add an extra flow that covers them as well. So we can have a flow parallel to this that takes care of, like it again fetches images, but instead of computing just hashes, it applies a neural network and then computes uses LSH to compute hashes. So the reason it's separate is because the load is quite different. In case of hashes, it's quite light, but convolutional neural network is more like it's heavier. That's why it's a good idea to separate them. How do we actually create this component? Where do we host it? One of the options is again AWS Lambda. It's tricky because if we use TensorFlow binaries are super big. and it's tricky to create a Lambda function that stays within AWS limits, because the limit is like 50 megabytes compressed, but TensorFlow is just too big. It's still possible to do it and compress after a few days of painful work. It's still possible. And if the load is not high, it's totally worth it, because we can score 1 million images with just $60. However, when the load is like 10 million images per day, it becomes expensive. It's like 600 per day. So better option is actually use EC2 machines from AWS or Kubernetes. So these machines are always up, because if there are, and for this reason, if it's just not so many images, it's more expensive, because all these machines are up and idle. But in case the load is high and there is always something, it becomes cheaper, and it will cost like 600, for example, for entire month instead of just one day. This is like for high load, like the multiple million images per day, Kubernetes is probably a better choice. And then finally, the big picture looks like this. So user uploads something, then the content and images go through this indexing process. And then by the time the content reaches the automatic moderation system, it's already indexed. And then we can ask the duplicate detection system, hey, like, what are the other duplicates? What are the other duplicate candidates? What are the other duplicates? In case when we are certain, we can right away reject these items. In case when we are not, we can ask moderators to reject and actually use the output from moderators, the feedback they give, to have a better model. That's all. Thank you.
All right. Thanks very much. Questions, anybody? Is this the only mic?
Hi, do you have any mechanism to guard against false negatives missed in the initial candidate selection?
Yeah, it's pretty difficult. Yeah, so like you have to, like you can include a lot more than you, like there is a trade-off, like how much computational power you want to invest into doing this. So of course you can have your candidate set very large, then you have to process a lot of things. So depending how costly is the mistake of letting a duplicate slip through, yeah, so there is no other way, just trying to score as much as possible. That's pretty, like it's a very difficult problem.
Yeah, thank you for your talk. Very interesting. My question would be, isn't this also prone for attacks? I mean, do you know of any like LSH distance maximization attacks or anything like that?
Yeah, so for example, like if somebody takes an image and takes a crop from this image, then hashes will already stop working. With LSH, it's like they are more resilient. But again, of course, there will be cases when like you can find an angle for which you rotate, and then neural network becomes like it doesn't notice it. For that, we can train CMEs networks. So try to do all this like rotation and all this manipulation with images and train a neural net to recognize these rotations. Then the hashes will be not just general purpose, like not just from the general purpose network, but something you specifically train for this particular problem. So this is the good next step after just using a pre-trained model, to actually have a special neural net that outputs hashes.
Thank you for the talk. I have one question concerning the images, because usually the websites are optimizing the images, and it can be heavily modified if they are uploaded several times, like downloading and uploading again. How resistant are the hashes to that?
So if you just take an image, open it in any editor and save it with a different compression, hashes should still stay the same. If you change small area, hashes should still stay the same. If you add a logo, like a watermark, some of the hashes will still stay the same depending on the size of this logo. But when you start cropping parts of image or rotating image or flipping it somehow, then hashes will stop working. But for these simple things like recompression, they will stay the same.
One question, the output of the CNN, why do you hash it? Can't you just like put it directly into Elasticsearch?
I don't know a simple way to do this to also be able to handle all these loads. Because like imagine that you need to insert like 10 million images per day to this index. And then you want to reduce your search space as much as possible. So with this load, it's kind of difficult. There are other things like FIs or Annoy that work directly on these raw vectors, but with high load, they become very slow. And to be honest, I don't know a nice way to put these vectors, like real vectors, to Elasticsearch. So hash is the simplest way.
Any other questions? No? Then let's thank the speaker again.